Hi, we'll continue with chapter 9. So with 9e, it's an application of anti-differentiation. You will have to separate the variables. So when you have a situation when your rate of change, you have a differential equation that will have two variables, you should be able to separate the variables. So you will have let's say dx f of x on the same side and dy gy on the same other side. Okay, then what we do is we transpose that on the right hand side. That gives you, when we anti-differentiate the integral of f of x dx, we'll get the y variables on the left hand side, so we get dy over g of y, and that will be your integral that you get on the right hand side. So we'll do a couple of examples. Solving that, this is just a direct application of the previous slide. So you have a differential equation. Notice you have a product of two functions in terms of x and y. You separate the variables, so you'll get the integrals e of x. Here you have an integrals in terms of y. As it is a reciprocal, you need to come up most of the time with reciprocal. So the situation you will use to anti-differentiate, you will use inverse circular functions, also log to the base e, and another strategies you have to think of is when you see a fraction with polynomial functions, questions you ask yourself, can I separate into partial fractions? Okay, in this situation here, it's a formula, it's a square plus 1, it's the inverse tangent, so that's should be easy to differentiate. But in other situations, just don't forget the other strategies. Okay, here exponential of x, easy to differentiate. Don't forget, using the chain rule, you get a 1 over 2 and you get a constant here and on both sides. Now that's c1 and c2, we can combine it to simplify into one constant. And the second part, so before we combine that c1 and c2 into one constant, and you will solve for y. If it's required, you make y the subjects, and that gives you a tangent function with an exponential, so it's a composite function. Alright, next example is really an application. So I advise you just to pause that video, read the whole paragraph, try to highlight what is required, what you know, express it into equations or expressions or constant, and also read every single question, what it's asking you to do. Okay, and then come back to this. So I'm continuing with this. First part is the first paragraph. It's, you had a 30-liter solution in a tank, but the volume is not constant. Okay, so you're running in how does it work out? I think, yeah, so you will have, it's leaking out 1 liter per minute. Okay, what I forgot as well in this, let me go back. So it's leaking 1 liter per minute, but it's the other way around. So it's getting 1 liter per minute of pure water, but it's leaking, it's running out 2 liters per minute. So the volume is actually a variable of time, it's not constant. So I would advise to write an expression. It's the volume in terms of t, is you start with t, you add 1 liter per minute, so it's 1 times t, and you're losing 2 liters per minute, so it's minus 2 times T. Okay, that will simplify to 30 minus T. Alright, another thing is the concentration, which is in liters. That's the concentration of the chemicals. It's E liters, which what you have. Knowing the expression of the total volume, the concentration of chemicals, which is going to be in it's a percentage, it's going to be the ratio of the liters of the X liters of chemicals divided by the volume at that given time. Okay, now, so that's going to be useful. Also, you leaking out a solution at 2 liters per minute. That tells you that you get a outflow rate of negative 2 liters per minute. Okay, so the way you're gonna resolve that, so you move on to, you need to show that differential equation. So keep those in mind. I'm going to use the same color code for this. So the rate of flow that is coming out is therefore the concentration, which is in as a percentage, so it's a concentration of chemicals, which is the volume of chemicals divided by the volume of the solution, with times the outflow. Because it's an outflow, it's going to be negative, and then you get this outflow of chemicals. Because we putting pure water in, coming at 1 liters per minute, the amount of chemicals coming in is actually 0, so it doesn't appear into that differential equation. Okay, so that's your final differential equation. That just consider what's the solution of chemicals coming out, as there's no chemicals coming in. With part B, so that's using that differential equation, you separate the variables, you anti-differentiate, so that's your respective integrals. You anti-differentiate, you get a log of E on both sides, you get 2 constants. To simplify, combine the constants into 1 on the right hand side. Set a value for the initial amount. So t equals 0, x equals a 0. So that simplifies and tells you the C constant that you have there is equal to that expression in terms of the initial amount. Am I in the way? Yes. So here, that's your C constant. Then we continue with that expression. We substitute that C constant, and we do the working out to get the general solution of x in terms of t, which is this final expression. Okay, still in terms of S0 and time. With part C, find the fraction of the original chemical still in the tank after 20 minutes. So it will be an expression in terms of S0, which is what we set as the original amount, so that's the original chemical S0, but the way it's asking you, it's a fraction, so you substitute t equals 20, you get x equals A0 over 9, and the fraction is x over A0, so that cancels out, that gives you 1 over 9, so the amount of chemicals is 1/9 of the original amount. And that's the way you word it for your for that part C. And that's it for today. See you.